Was as well IRC, and structural analysis was carried out using STAT, Pro, Midas and LARSA 4D. Here for every stage of design, we had to check the forces, and the bridge had to be designed for all the stages. In fact, we could say that it was a four-dimensional design where time was the fourth dimension. A very high strength grade concrete was used. Slabs and piers were all M50 grade, pedestals were M60 grade, pile caps and pile were M35, and high tensile steel was used for fabrication of the steel girders and towers. We are talking only about the ROV proper. This bridge, ROV proper itself had more than 10,000 cubic meter of concrete. 1.5 meter dia piles were used, and high tensile steel was 2,000 tons, out of which, and total steel was 2,000 tons, out of which 1720 was high tensile steel. This is a view, snapshot of the bending over diagram under dead load condition. This is under live load condition, the critical loading condition. When we talk about the stages, first of all, the pile foundations are cast, then fabrication yard is set up for fabrication of girders and for the main span and the pylon towers. The common piers are constructed. Temporary trestles are required to be erected for the back span, and this had to be in service till all the cables were stressed. RCC back span was cast over the trestles. Then steel pylon towers were erected. Thereafter, the main span was erected. First and the last panel of the main span were erected with mobile crane, and the second to ninth panel were erected with the help of deck erection crane. Once the whole slab was cast, again the stressing of cables were carried out for adjusting the forces. Because of very massive construction of RCC, as we can see, the pile cap is 413 square millimeter in plan size. The common pier 1 itself is 111 square meter in plan size. And the back span, which was constructed over trestles, is 2,000 cubic meter. For this type of construction, we needed very specialized precautions for manufacturing, transporting, and placement of concrete. And for the massive back span, a very massive staging arrangement was required. This is the location of the common pier. Before construction, there were a few trees and an office. This is the casting of common pier 1 is going on. We can see the trestles have been erected to support the reinforcement cage and the shuttering. Because of safety point of view, these trestles had become very important. The casting of pier had to be done in about 2.5 meter lifts. Because of excessive weight of the concrete, it was not possible to keep the shuttering intact, and also it would have affected the concrete in the lower layer. This is the site of common pier 2. This is the site of the pylon location. The pylon has bottom part as RCC, and over that deck, 3 towers were erected. The pile cap length is 37.9 meter, and its width is 10.9 meter, and the piles were 1.5 meter, dia 35 meter long. The design load of the pile was 840 ton, which required massive load testing arrangement. This is a view of the pile cap casting work. As I told, back span, that is the main span which were acting as anchor, was cast monolithically along with the piers and the deck. For this, very sturdy arrangement was required. The staging was supported on concrete foundations, which were designed to bear the 800 ton load of the staging and 5,200 ton load of the back span, apart from the construction equipment and materials which were required during construction of the main span. This was cast in 2 parts with a properly designed construction joint. 3 pumps were working round the clock for more than for about 35 to 40 hours. and 30, with total average capacity of 35 cubic meter per hour. And we had to use ice to cool the water of the batching plant so that temperature after pouring does not become excessive. This is a view of the backspan construction. We can see the formwork tubes for the cables and massive staging arrangement. These are the concrete pumps are working round the clock, and so many transient mixers are required. The pylon towers were constructed in the form of 10 segments. Each segment was erected with a tower crane. A heavy-duty tower crane was imported from China. It was then load tested at 39 meter and 19 meter radius. Each section of the pylon, the base section of the pylon was placed and fixed with extraordinary care, because it was the guiding factor for the entire alignment of the 55 meter tall steel tower over it. The second section was slid into the splice plates, which were fixed to the bottom section. Till about 15% of the holes were filled with drifts and a few black bolts. The section was kept in holding position by the tower crane, and then the HFCG bolts were filled in the balance holes. Thereafter, one by one, the drifts were removed and HFCG bolts were fixed. This is a view of the load testing with tower crane. The tower crane was self-climbing time. After a certain height, it could erect itself. This is a view of the erection of the pylon. We can see there are so many bolts. At each joint, there were 400 bolts. This is a perspective view just before construction of the main span across the tracks started. The construction of the main span required a deck erection crane and mobile cranes. The deck erection crane was manufactured in the fabrication yard itself. It was a 16 meter by 33 meter rectangular frame moving over 4 tower legs, which were moving on the rollers. It had 2 rails over it. Over the rails, a cross frame would move, and over the cross frame again there were 2 rails over which the hoist would move. With the help of hoist, we could take the material to any point.
Can you please conclude, please? 2 minutes.
Just 2 to 3 minutes, sir. After the steel work was complete, the panels were, then the cables were erected and stressed. And after that, precast slabs were erected, and thereafter concreting was done. Regarding precast slab, it has already been covered in the third paper of the session, so I will not talk about that. There is 40 meter length track was made for movement of the DC. The DC was used for the panel number 2nd to 9th. A typical cycle for erection of the panels was 27 days, and we can see in serial number 7, 14 days were required only for curing and moving, and this was the main factor why it took so long to erect the main span. The stay cables were brought to the site for fixing in the form of a reel, which were uncoiled with motorized uncoiler. And geometric control was required to be carried out at each stage. And there were about 2 to 3 instances when, as per geometric control, the cables had to be re-stressed. This is a view of the stressing arrangement. We can see there are anchorages, blue color duct welding. For the bridge health monitoring, sensors were fixed in certain strategic locations. Dampers were used for long length cables. Power blocks and traffic blocks were required when the movement was done over the track. This is a view. Here we can see there are 9 numbers of tracks, and these tracks are located at nearly 50% of the joints. And for these 50% of the joints, we required traffic and power blocks. For this, detailed planning was done. On 25 days, blocks were required of 2 to 5 durations, spread over for 200 days. And the work was done absolutely as per the plan, and the railway, in fact, appreciated that all the their operations were not affected at all, even with this 200 days of operation. A platform is there for fixing of bolts. The deck erection crane is moving across the track. The precast slabs have already been covered in previous paper. I'm not talking about that. But these were specialized precast slabs which were cast over vitrified tiles for perfect accuracy and finish. And they were tested during the trial assembly in the yard so that during erection over the track, there is no problem encountered. A wind tunnel study was carried out by CRRI and nothing susceptible was found. It was done on a scale of 1:40 model scale. This is a view of that. Very high accuracy fabrication work was involved because the stresses were to be transferred through end plates which required perfect finish. And the pylon towers have to be erected without any misalignment. This is a view of the fabrication yard. Submerged arc welding was carried out, and in some of the locations where it was not possible, MIG welding was done. A diversion road and remodeling work and several relocation of potholes are carried out, so we have to create the site for executing this work. Safety awareness drives were required to be carried out throughout the project, and even a full-fledged safety week was observed because safety consciousness had to be kept alive in the workforce. Several tests were to be carried out on the stay cable material. The stay cables material, the strands were manufactured in India itself by transfer of technology from France. And during their manufacturing, all testing were carried out in our presence. Since this project requires very complex structure and painting could not be done frequently, so very long life painting scheme was adopted which required 60 micron surface roughness, which could be achieved only with copper slag. And 3 coats of special paint was applied. This is a view of the paint shades after each coat. That's all. Thank you all, and Jai Hind.
Thank you, Mr. Singh. Then, next paper is composite corrosion protection system in rehabilitation of steel structures in corrosive environment. A case study by Ms. Ishita Manjrekar, Shri Raghuveer Salkar, Shri Saurabh Manjrekar, and Shri Abhishek Salkar. The presenter is Ms. Ishita Manjrekar. You have 10 minutes.
Okay, sir. Ishita Manjrekar is the Director, Technology of Sunanda Specialty Coatings, a 40 years old construction chemical company. She is recipient of many awards, including Young Concrete Professional 2016 award. It's a global award given by American Concrete Institute. So, Ishita, you have got just 10 minutes to go.
This is the last paper in this session. I know you're all getting impatient for lunch, but just bear with us because of the time which was taken off by the opening function. We have to eat into the lunch break. Thank you.
Good afternoon, everybody. Thank you to IRC for this opportunity, and thank you, dignitaries in the dais. The topic of my talk today is modern-day corrosion protection technologies. I'm going to talk about case studies, 2 types of case studies. One is for corrosion protection of post-tensioned RCC bridges, and secondly, for corrosion protection of structural steel bridges. So the agenda is first to talk about RCC bridges. I'm going to talk about a 50-year-old corrosion protection technology that is being used globally as well as in India. Specifically, I'm going to be talking about the use of bipolar migratory corrosion inhibiting admixtures as a corrosion protection system. I'm also going to talk about case studies of various bridges, major as well as minor bridges across the country today, various state PWD, railway and metro bridges that are utilizing this technology successfully. Finally, I'm going to talk about testing and results to do with these projects. The second part of my talk is going to be about corrosion protection, preventive strategies as well as restorative strategies for structural steel bridges. The case study that I'm going to focus on is a bridge in Usgaon, Goa, owned by the Mineral Foundation of Goa. Once again, I'll talk about the treatment methodology and finally conclude with conclusions as well as findings. A little bit about the perspective from which this paper is coming. I work for a construction chemical manufacturing company, and I'm a chemical engineer by training as well. So it's a very humbling experience for me to be amongst all of you top designers, civil engineers, planning authorities and bodies. And I'd like to, in all humility, present a little bit about the materials aspect of construction of bridges. So I want to talk about corrosion, concrete, certain admixtures, certain technologies, materials specifically that can help aid to increase the service life of these very, very important assets that we're all constructing. Sunanda has typically had a history of product development and innovation. We have been regularly receiving awards for Product Innovator of the Year from the Ministry of Chemicals and Petrochemicals, Government of India. So the past 3 years continuously we have won this award. And it is based on this research and this original work that I'm going to be sharing with you today. So a little bit about modern RCC structures or bridge structures in India. Large-scale, high-speed construction has made using RCC technology or materials a choice for bridge construction because of its reduced cost and ease of maintenance. However, when we talk about RCC, one of the most important concerns, especially with India having such a large coastline, becomes durability or rather corrosion protection of these structures. So India roughly loses about 2 trillion rupees, which is about 4% of our GDP every year due to corrosion of infrastructure. This here is a diagram or a graph that was originally proposed by a scientist called Tuti. So what it does is it plots corrosion damage versus time on the x-axis, and it's juxtaposed against the cost. So as you see in the beginning, during what's known as the chloride contamination period, there is almost no visible damage to the structure, and this is where corrosion is in what is known as its initiation period. Over time, as the structure begins to get contaminated with chlorides, the corrosion process of visible damage to the bridge begins to be seen. What you see in these yellow dots here are the various repair cycles. So repair cycle 1, 2, and 3. So each repair cycle, what it's trying to do is bring down the damage, of course, at an affiliated cost. So each consecutive repair cycle brings down the damage to a certain extent, but all it's doing is the cost at which this damage is being brought down is increasing over time, and finally it's going towards the end of its inevitable end of serviceability. The idea behind preventive maintenance is to increase rather this period, the chloride contamination period or the initiation period of the bridges, to maximize our lifespan. I have here up on the next slide actual data presented at the 17th US-Japan Bridge Engineering Workshop in Japan. This slide conveys a very powerful message. What it does is it plots the service life of coastal bridges in the country of Japan. Now, when we design bridges, when all of us design bridges, we're talking about 100-year service life as far as design is concerned. However, on an actual plotting of service life of coastal bridges, it was seen that most of the bridges in the country of Japan had a much compromised service life of between 0 to 30 years for the most part, with a few outliers going to, 2 plots here you see on about 50 years. This again becomes a very concerning situation. So what Japan has done is they've basically gone ahead and classified bridge structures and mandated that certain bridges which lie within so many meters or so many kilometers of the coast have to have preventive corrosion protection technologies implemented right at the construction stage. So they have classified their bridges lying in region A, region B, region C, and then each region has its own set of guidelines for designers as well as constructors and owners to follow as they make these bridges. Coming to the corrosion map of India, of course, this is a map that all of us have seen many times, but what I want to basically point out is this very large coastline that requires our attention as we talk about bridge structures in our country. I want to quickly talk about some of the conventional corrosion protection technologies that we're using today. So usually, our first line of defense, or the first thought that comes to mind when proposing a corrosion protection system is to coat our steel rebars. Now, coating of the steel rebars, of course, makes, I mean, it's been around for a while, but I think over the past 30, 40 years, there's a lot of literature that has begun to highlight some of the shortcomings of coatings as a corrosion protection technology. Essentially, using coated rebars makes us vulnerable to problems associated with pinholes in these coatings, defects in the coatings, defects that come about during transportation, during storage of these coated rebars at site. So as you can see from the photo here on the right-hand side, even though these rebars are coated, there are some slight defects or some defects which ultimately lead to failure of these rebars. This has been documented in multiple papers, when postmortems were carried out in certain bridge collapses in California, in Florida in the 80s and 90s.